All right, what's going on? Today we're going to be doing another LeetCode problem. This one is called remove nth node from the end of list. So let's get into it. So we're given the head of a linked list, and they want us to remove the nth node from the end of the list, and then just return the head of that list with the dropped list node. So basically, for this example, we're going to have the head of a list, right? So we're going to have the pointer to the head of a linked list, and then we're going to have an integer in. They want us to remove the nth to last element. So like for this list, we can obviously see all the nodes, which is kind of cheating, but this fifth node here would be the first to last element, and then the fourth node here would be the second to last element, and so forth. So when n is 2 here, they want us to drop this node here. That's second to last node. So yeah, let's just go ahead and get into the whiteboarding for this problem. So let's say we had and let's first talk about an edge case. There's one edge case for this problem, so let's just get that out of the way first. So if we had a list of size 3, so if there were 3 nodes in our list, obviously that last one will just be pointing to null. If n was equal to 3 here, they would want us to remove, right? This is the first to last element, this is the second to last, and then this is the third to last element, right? So they'd want us to remove this one actually. So when that happens, we can't just, like, normally we would want to, like, if we were removing this 2, we would just want to move this pointer here to here, right? But the problem is when we're removing this first element, there's no node over here, right? So it's like, what do we do in that case? Well, this is an edge case. So I'll show how we would handle this just by beginning to step through our algorithm. So for our algorithm, we're going to have a slow pointer and we're going to have a fast pointer, and both of those will be pointing to the head node at first. So the first portion of our algorithm is going to be just shifting our fast pointer forward through the list n times, right? So moving this fast pointer down n times, we're going to do this with every test case. So it wouldn't matter what n is or what the list is. So we're going to move fast down 1, 2, and then 3. And then notice what happens in this edge case. So the fast pointer, when we're removing the first node for this edge case, the fast pointer is going to be pointing to null, right? So we can basically check if the fast pointer is pointing to null. We basically just want to return a pointer to the second node from the head. So we can literally just return head next, and then that will basically return a list just starting from that second node. So effectively that handles the edge case. But let's look at a different example and see what happens, with the full version of this algorithm. So let's go ahead and do a little bit of a bigger list here. So we'll do n equals 2, and then I'll just do a list with like 5 elements or 5 nodes. So if this was our list, we'd basically, we'd start the algorithm the same. So we have a slow pointer and we have a fast pointer. And then we're basically going to move our fast pointer down by n times, right? N nodes. So 1, 2. So our fast pointer is going to be here. And then we can check for the edge case at this point. Is the fast pointer equal to null? It's not, right? It does have a node there. So for the next part of the algorithm, we're just going to want to loop while, and let me make a note of this. So we're going to want to loop while our fast pointer next is not equal to null. So this is kind of the final part of the algorithm, or not final part of the algorithm, but the next part of the algorithm. The algorithm's not too long. There's only really one more part after that. But so while the fast pointer, while the next list node from the fast pointer is not null, we're gonna slide both of these nodes along by 1. So one iteration would be, we're gonna move this fast pointer here. We would move the slow pointer here. That's one iteration. Fast next is still got a list node there. So we're gonna move these down again. And now notice that fast next is null. So we would stop right here. So let's just erase this. So we know our slow pointer will be here and our fast pointer will be there. So I'm just gonna write that. So our slow pointer will be there. Fast pointer will be there. And then if you look at where our slow pointer is, you can see that it's right before the node we need to remove. So we can simply, for the final part of this algorithm, to drop this node, we can just set whatever the slow pointer node is pointing to next. We can just set that to slow pointer next, and that'll just skip over this node, essentially. And then we can return a pointer to the head of the list like normal, and that'll be the desired list with the nth to last node dropped. So that's pretty much it for the algorithm. So of course this is going to be linear time complexity, right? Because in the worst case, we're just iterating over each node in the list. So linear with respect to the size of the list, and then the space complexity will just be constant because we're just going to have 2 pointers, and that's it for the space, regardless of input size, regardless of the size of that list. So yeah, let's just go ahead and get into the code here. It's pretty straightforward for this problem. So we're going to have a pointer to a list node for our fast pointer. Both of these will be head at first. We also need one for the slow pointer, also set to head. And then we're gonna just loop. We're gonna want to iterate n times, right, to shift that fast pointer forward in nodes down the list. So while I is less than n, I plus plus. We're not even going to be using the I, but I find this C style for loop to be a simple way to do something n times. So nevertheless, yeah, we're just going to shift this fast pointer down n times. So fast equals fast. Next, we're just going to do that n times. And then basically, for the edge case, remember if fast, so we can just have an if statement here, if fast, or if not fast, really. So if fast is equal to null pointer, we can just return head next, because if that's the case, we know the element we need to return is the first one in the list. So we can literally just return a pointer to the next element from head, and that'll be the list excluding the head, right? So that's how we're going to handle the edge case where we're removing that first node. Otherwise, we're going to loop while fast next, right? While that is a list node, and while it's not, while it isn't null, right? So we're just going to shift the fast pointer down by 1, down the list by 1, and we're also going to shift the slow pointer down the list by 1. And at that point, our slow pointer will be right before the node we need to remove. So we can simply point slow next instead of pointing to whatever it's pointing to next, because we want to drop that node. We're just going to point it to slow next to skip over the slow next node. Right, so that's pretty much it. We can just return the head pointer to the beginning of the list, and that'll handle every other case. So that's pretty much it for the code here. I think this, for a linked list problem, this one's pretty straightforward. So we beat 100% with runtime and then 60% with memory. So pretty optimal. We're not using any extra space, and right, again, runtime's linear. So hopefully this video helped you understand this problem more. If it did, leave a like and subscribe, and I'll see you guys in the next piece.